The recording is on. So today we have Gala, and he will introduce us to um, cloud analysis a little bit first, which is quite important for climate science, and talk about the challenges in the data labeling in this field. So Jay, um, we're we're here. Thank you.
No, thank you. So I'll start. So the talk is from my paper, Adaptive Labeling for Enhancing Remote Sensing Cloud Understanding, from the NeurIPS 2023 workshop. That is the TCCML workshop. So first I'll you know uh, go to the slides, and then we can see the different challenges that are faced and what exactly is cloud understanding, cloud segmentation, and then how we try to solve it. Right. So the problem is that given a satellite image I, cloud detection predicts a pixel level binary classification of whether each pixel is a cloud or not, outputting a binary mask M. So every value in the mask M is essentially just a 0 or a 1, right? So the pixel 0 will indicate that it's not a cloud, and 1 will indicate that it is a cloud, right? So formally, training data set D-train contains image mask pairs, that is IM, that are used to train a cloud detection model, which is then evaluated on a testing split, these tests. So nothing fancier, the same thing that we do in any segmentation or classification task. You have a training data set, you have a testing data set, and then you have a mask to test it with. Right? So that's the thing. So what makes cloud understanding so important and so difficult is that cloud understanding is a critical component of weather and climate science, and it impacts many sectors like disaster management and weather analysis and stuff like that. Right? So, but achieving fine-grained cloud analysis, such as cloud segmentation in remote sensing, remains a challenging task due to the inherent difficulties in first obtaining accurate labels, and second, because working with satellite images is difficult in itself, because you don't have simple RGB images always. You have images that have multiple bands, and each band corresponds to a specific wavelength in the atmosphere. So there are two problems. First, uh, labels. So you don't have many accurate labels. And second, you're working with more than 3 dimensions of the images. So that is the problem. So what we try to what we tried to initially do for this work was to basically use transformer based methods to advance cloud detection, because what we saw in our literature review is that people were not making use of the advanced techniques like transformers. And since we knew that transformers have been able to perform very well on vision tasks, especially after vision transformers came and then swim transformers came, so we wanted to make use of those capabilities and see if we can push the state of the art, right? So in our initial experiments, what we found out with using mask former from Meta, and then mask 2 former, then seg former, and also Kubernetes from different labs, is that the results were poorer than the CNN based models. And even though CNNs were considered quite bit on the inferior side, they seem to perform better on the task, right, than transformers. So then we had to go deeper and then evaluate and analyze the data set itself to see if there were any problems within the data set, and analyze if it is a general problem within the entire cloud detection domain, right? So that is what we did, and we'll explain how our method or how our approach works in the upcoming slides. So before we move on to that, I will take a few moments to set the premise and to to basically help you understand how the traditional methods work and how our method kind of builds on top of that and advances the domain. right? So the traditional methods can be divided into three categories. First is threshold based, second is machine learning based, and third is deep learning based, right? So yeah, the threshold based methods rely on differences in scattering intensity between the clouds and atmospheric particles in specific spectral bands, right? These methods work well only when clouds have high visible reflection and cooler infrared temperatures compared to the Earth's temperature. However, the performance of these methods depends uh, purely on prior knowledge and contrast between the clouds and the Earth's surface. So let's say if there was snow inside in the image, and if you're looking from top, so my hand is the satellite and this hand is the surface, right? And there were clouds in between. And if this hand on this hand there's snow, then it's very difficult for the model to distinguish between snow and cloud because they look very similar, and it's difficult even for humans to do that, right? So these threshold based methods were difficult because they were not difficult. It's just that they were not as accurate and not as reliable uh, when it comes to detecting clouds when there are aerosols or snow or dust or smoke particles in the area, right? So that was threshold based methods. Then came machine learning based methods. So then we saw the rise of models that depended on support vector machines and random forests, which leveraged the texture features from the images and tried to build relationships between the images and the labels, right? But the problem with those was that they relied too heavily on handcrafted features. So what experts and scientists would come together, and then they would decide on a few features that would be important for the classification, and then they used to hand I mean write them by hand, right? So it worked in few cases, but it did not generalize well to other cases, correct? Then came deep learning based methods. So deep learning in itself became popular because it eliminated the need for developing handcrafted features, right? So if in general, even if a model has to predict whether there is a cat or a dog in an image, you don't really have to specify, or you don't really have to write the features for a cat's mouth or a cat's eyes or cat's ears, right? The model is powerful enough and capable enough to learn those features by itself. So that is why deep learning methods took off. But then again, the problem with all these methods is that they assumed that the data that you are working on is very clean and it's very accurate, right? So if you were in a box, assume if you were in a box and you could jump as high as you can, but the box has a certain limit. The box has a lid, right? So your jump will only be limited by the height of the box or the height of the lid, right? You cannot jump higher than that. So in this sense, the box and the height of the box is basically the unreliability of the data set, the noise in the data set, right? So that is what I'm trying to make a point about. So noise. So what we noticed in general is that there is a lot of noise in in cloud segmentation data sets because of two problems. First, the images are too complex in itself, and second, obtaining good annotations, good labels is difficult in any domain, be it medical or be it satellite images or anything, right? So cloud annotation is a challenging task, and previous methods assumed the availability of reliable segmentation annotations without considering the noise in the dataset. So if you see, there are two examples on the screen. There's one image one, and then the corresponding mask, and image two and the corresponding mask. So if you look closely at image one, you'll see that there are a lot of clouds in the image, and but the mask is clearly not able to pick all those intricacies out, right? So the mask is basically labeling everything as a cloud. All the white spots are cloud, and on the black spots are non-cloud, right? So the mask is basically very inaccurate, and it is labeling everything as a cloud. Now, I mean, just to put things into perspective, these satellite images, they are huge, right? They are not our standard 256 by 256 or 512 by 512 images. These are in the scale of thousands and hundreds of thousands of pixels, right? So, and the image that are on the screen, these are not the entire images. These are actually small cutouts from those huge images, right? So you can imagine how difficult it is for a labeler or an annotator to annotate such intricacies. So that is a major problem in general in the cloud data sets, right? So to tackle this problem, we proposed an algorithm that is we call cloud adaptive labeling, which is an efficient module that enhances cloud detection approaches by acting as a and in a post-processing block to relabel existing noisy cloud labels into a refined version. So in simple terms, what we do is whenever you are training a model or whenever you're fine-tuning a model for cloud detection, you can basically add a, cal step or a cal step to refine the labels that you already have, assuming that those labels are not very accurate and it needs some sort of a refinement. So the refined labels will have better chance of improving the model's performance. So that is the idea, and I'll show you how this works. So before I explain how cal works, I'll also show you how binarization works, because that's a very important step of cal. So when I say binarization, it's exactly what like you basically divide a picture, all the pixels in the picture as 0 or 1 based on a certain threshold. So let's say the highest pixel value in your image is 255 and the lowest pixel value is 0, right? And you decide that the threshold that you want for the binarization is 50. So every pixel inside the image that has the pixel value greater than or equal to 50 gets assigned the number 1, and all others become 0. So everything that is north of 50 becomes 1 or white, or it is shown as white in the final output, and everything that is not greater than 50 becomes black, right? So we try to learn a a dynamic pixel threshold value for the entire data set, and we basically use the learnings from the threshold based methods that I described earlier, and we basically make it trainable. So instead of training the entire data set on one single threshold that may or may not be suitable for all images, we let the model decide, we let the algorithm decide what threshold is most suitable for what picture. Right? So in that, it generates better labels and better masks, right? And so I'll also explain how the algorithm works line by line. So first, we set a learnable threshold. So this is the first line that is set to 60. That is just the starting number, right? So we start at 60, and then we let the algorithm decide wherever it wants to take us, right? Then there's a delta x. Delta x is basically how much you want to change the threshold. So here we are changing it by 2 units. Then you also keep a track of the best loss, because that will be used to control the learnable threshold. Do you want it to go up or do you want it to go down for a particular case or a particular image, right? Then we have a lower bound and an update frequency. So lower bound is basically the minimum threshold that you would like to go to and not beyond that. And the update frequency is at how frequently do you want the updates to the threshold happening. So here I've set it to 150, and that will be 150 iterations, not 150 epochs. Will have a change in the learnable threshold every 150 iterations, right? So, and then you have a simple learning or a training loop where the first line says that new labels is binarize the image, and the threshold for the binarization function is basically the learnable threshold. Correct. So what you do is in the first line you create new labels, and then you do a simple forward pass where outputs equal to model, then the images, then you have the loss function, then you check if the loss that you got is that the best loss so far. And now what you do is, now if you check the if else conditions, now this is where the algorithm will now update the learnable threshold, right? So if the loss is greater than the best loss, then what you do is you will decrease the threshold. Correct. So essentially, what I'm trying to say is when loss is greater than the best loss, it means that you are not capturing enough clouds, right? So there were clouds in the image, and then you missed them. So you want the threshold to go less, correct? And in the opposite case, it's different, right? It's the opposite. So you are basically labeling everything as cloud. You are also labeling things that are not cloud as cloud. So please increase the threshold. You don't want everything to be included in the cloud region, correct? So I also have a slide where I'm basically I will try to explain how the threshold affects the final output, right? So on the left hand side corner, you will see that you have a simple satellite image where there are many distinct clouds. You can see that, and then we will see what happens when I change the threshold value from 250 to 255 to all the way down to 100, right? So when I start the second image, when I start, the threshold is set to 255. Basically, the threshold is the highest, and there are no values that are higher than 255. So everything gets assigned as a non-cloud, correct? And then when you lower the threshold, you go down to 215, if I'm not wrong. So yeah, you go down to 215, and you see that some clouds are being classified here, right? Then when you lower the threshold to 163, on the bottom left, you see that some more clouds are uh, getting recognized. And then when you move it to the second last image is at 150. So you see that even more clouds are being recognized, but then there are also certain small pixels, say in the bottom left or in the middle left region, that may or may not be clouds, but they are getting picked up because the threshold is too low. So everything that is north of 150 gets assigned to a cloud class, right? And in the right bottommost picture, you will see that almost everything is being classified as a cloud, and almost nothing is now land or non-cloud, right? So that is how the threshold impacts the labels inside an image, right? And the point of the algorithm is to identify the best. And so this is the point of the algorithm, to identify or to learn a best or a most uh, optimal threshold value for the entire data set. And if you have any questions, please feel free to interrupt me at any point throughout this slide. Uh, I'll be happy to help. Yes, there's a question.
Yeah, I have a question. Given that the point is to find the best threshold, is there anything else that would give the same result as the clouds that can be mistaken for clouds on the picture?
I didn't understand the question. Can you please repeat?
So the clouds are the brightest in a picture, as I understand it. And are there anything else that can be in a picture that would be mistaken for a cloud in this algorithm?
Yeah.
Like,
So
yeah.
yeah. So let's say you have snow in the image, and it's very difficult to work with snow, and then but to but see, if you have snow, or if you have dust, or if you have smoke, even smoke sometimes gets misclassified as clouds, right? So to uh, handle those cases is challenging in itself, even for human evaluators. But for cal, I mean, of course it will not take every single value. It will not capture every single cloud or non-cloud case, but then it helps because if you see the the reflection of snow is different on different wavelengths as the reflection of a cloud. So if you have images that have multi bands, that are not just RGB. In our paper, we only work with RGB, right? So if you have more than 3 dimensions, if you have more wavelengths, then you can capture those as well. So you can capture, so you can have a threshold for the wavelengths also.
I see. Thank you.
Okay, so moving on, how do we use Cal and train the models, right? So we understood how Cal works, but how do we actually integrate it with the models? So there are two ways you can work with Cal. I think I missed this slide. Yeah, sorry, okay, I'll come back to this later. Yeah, so there's actually two ways in which you can work with Cal. So one we called hot and one we called cold, right? So in hot, what you do is you train the any model that you have. Maybe you have a unit, maybe you have an FCN, maybe you have a transformer based model. Whatever model you have, you train it with the actual data set that you have. In actual, when I say actual, I mean the actual noisy data set without any refining. Okay, so you train the model with whatever data set you have, even though it is noisy, and then you retrain it by using CAL. See, so the idea here is that the model already knows some features because not all the images the inside the data set may be noisy, right? So the idea is to let the model learn a few general features of what are clouds and what are not clouds, and then if it has a general idea, it we see that it performs well after retraining with CAN. So if you see, there are two paths here. Path one, in path one, what you do is uh, you use CAL directly in the first step of training. That is called the cold method, where we don't retrain the model. We simply just integrate CAL in the first step of training, right? In the second step, that is the one that I was mentioning, that is hot. In the hot method, what we do is we first train the normal model with the normal data set that we have, and then we use CAL to retrain the model. So you are basically fine tuning the model on refined samples or refined labels. So that is one another way of doing it. Okay, so the advantages of CAL are pretty straightforward. It enhances performance. It eliminates the need for a prior estimation of an appropriate threshold. That was the case for older methods that depended on a fixed threshold by some expert, right? Third is that it is model agnostic. You can plug it and play with any model that you have, and it works well. It is known to improve the performance of that particular model because because we are not making any architectural changes to the model or anything. We are just refining the data set. And if you have a general idea about deep learning, uh, we all know that deep learning performs well when you have cleaner data sets, when you have good quality of data sets. So even if you have hundreds and thousands of images, if they are of poor quality, you will see a drop in performance eventually. So that is the whole idea, that improve the quality of the data set to improve the performance, right? And second, we also see that there is a faster convergence after you use CAL, and it stabilizes the performance metrics, right? So I'll show you the graphs also. But before that, let's just have a look at the numbers. So you see that CD, CTFM, then there's LWCDNet. That was, I think, the SOTA at the time we published. Then you have simple FCNs, deep labs, UNets, and the the main metric to focus on here is MIOU. So MIOU is the mean of the IOU. IOU is intersection over unions, which is actually the main metric to to evaluate models on when you are talking about segmentation tasks, right? So if you see that the normal unit has an MIOU of 73, whereas the unit plus cal, that is the retrained version of cal, that is a hot method, it gives a 93.15, which is actually a new SOTA. So it forms very well on any model that, and we ran multiple experiments to show that this is model agnostic. And uh, when we say model agnostic, we can also say that you can apply it to any data set as well, right? So it is data set agnostic also, if that is something. So here are simplified tables to show that cal improves the performance of models uh, by itself. And when I said that it performs faster conversions, yeah. So we have this also. So on the right hand side, we have results from uh, yeah, sorry. On the right hand side, we have results from non-cal, and the left hand side is results from cal. We also said that it stabilizes the performance metrics. So on the left hand side, we have non-cal, and the right hand side we have cal. So I'm at the. I mean, these are the slides I had for the session. If you have any queries, you can contact me on my email, and the QR code here given for the code may be a bit old. So please refer to the code link that I've given in the chat. The paper link and the old slide links are also given in the chat, and I'll provide the new slides to one of the hosts later after the meeting. If are there any questions? How's the performance on Sentinel to SR data? Sorry, Sentinel, we have not tried on that data set. But you can try cal on that data set and let me know how it went.
Thank you for the presentation. Could you go to the algorithm part again, the training algorithm that you showed?
Yeah. Yeah.
Yeah. So in the network, there are two trainable components. One is the in your first algorithm itself, there are two trainable components. One is the cal part, and the other is the actual model itself. Right? Am I right?
Right.
Or
Right.
okay, how are you computing the loss of these two? Are you doing gang kind of thing, training one thing in one loop and second thing in second loop, or doing the loss on both of them simultaneously? How are
Yeah.
you
So
computing?
right. So both of the losses are separate. We are not using one's loss for the other. So when you see that we on the third line of the loop we have loss equal to criterion outputs and new labels. So that is for the model, and the
Okay.
model is trained on that loss only, right? And
Yes.
uh, and when we say that we are also learning a threshold, we are only updating the threshold values here itself. So there's no backprop or no
Okay.
gradient
Yeah.
kind of an update for the learnable threshold.
Okay. Okay. Got it. And could you go to the results part, the metrics that you were showing?
Yeah.
Yeah. No. No. A little bit backward. Again backward. Yes. So here, when you're comparing the vanilla unit with your unit plus cal, are you using the same configuration as that was used in the unit vanilla unit one that you are referring? I mean, just
Yes.
adding cal. Okay. So
Yes.
so only this and the 38 cloud data set, like you said, the cloud data sets are usually very noisy. So on which one you trained for this benchmark and on which one you tested? So it seems you tested on 38 cloud, but you trained on 38 cloud itself as well.
Yes. We actually divided the data set in two parts. So D-train and D-test come from the same distribution.
Okay, but the labels that the unit is seeing due to CAM, your algorithm, it's not the same one during the loss computation. as what is the actual label, because there would be some kind of thresholding applied due to this scan algorithm. So I'm just curious, why that thing is actually performing better, and also during inference, you still use cal, or during inference you remove the cal part.
No, during inference, remove it, because if you train it using one method, that I mean, see, if you are retraining the model using cal, and then you are also, I mean, you cannot mess with the test, right? You can, the test remains the same way, that is untouched.
Okay. So basically, during training, you use unit plus cal, and during the testing, you use the actual labels that were there
Yes,
for comparative metrics. And using cal as some kind of a guidance, you it actually made predictions on the actual labels better. Not just because the labels that you trained on, they were kind of, in a sense, synthetic labels, because you applied
yes,
kind of thresholding.
right.
Okay, that's very interesting. Okay, thank you very much.
Yeah. Do we have any other questions?
I think that's all.
Okay.
All right. Well, thank you, everyone. I guess we're going to finish here. Thank you, Jay, for presenting. It was very nice. All right. Thank you, everyone.
And just one last thing. Thank you, Kate, and thank you, Jen, for organizing this event. So this is my first. I've never done speaker sessions before, so I'm really grateful for you inviting me here. I had an amazing experience, and I hope we can do this again someday.
Well, I'm glad. I hope your first speaking experience went well, and please join our other sessions too if you're interested.
Definitely.
That would be great.
Definitely.
All right. Thank you, everyone, and thank you, Jay, for presenting.
Okay. Thank you. Bye bye.